Hey everybody, let's talk about predator-prey models. Now remember when we first talked about coupled differential equations, we said that they could be used to model predator-prey scenarios because as the population of one animal increases or decreases, so does the population of another animal over time. And there are three variables: the one animal, the other animal, and time. Now remember, a rate of change, in particular dx, dt, or dy, dt, is an amount of change over time. So we're looking at how a population grows over time, and also how those population growths and declines are connected with the population growth and decline in another species. So let's take a look at this scenario here, which you see on your slides. It tells us that the population in thousands of fish, which is our x variable, and of sharks in hundreds, which is our y variable, at time t, this is being measured in years, are given by these equations. All right, so the derivative of x with respect to t, in other words, the rate of change of fish over time is equal to 3x minus 3xy. Let's interpret that. The rate of change of fish over time equals 3 times the number of fish minus 3 times the number of fish times the number of sharks. That is what this right here is saying. Similar for the rate of change of sharks over time. So the rate of change depends on both the population of sharks and of fish at any given point in time. So we've got a question here that says find the two equilibrium positions for the populations of fish and sharks. Initially, there are 3,000 fish and 20 sharks. So we need to understand what equilibrium point means. An equilibrium point is when the populations are the same, right? When they are both sort of at peace, so to speak, right? They both have enough. In other words, when neither of them are growing or declining. So what that means is that we want to see, we're going to set each of these derivatives equal to 0. By derivatives, I'm referring to the differential equation. So remember, dx dt is x dot, all right? So we have x dot equaling 3x minus 3xy, and y dot equaling the other rule, xy minus 2y. Well, when the rate of change, when the population is neither increasing nor decreasing, that means dx dt and dy dt equals 0. Let's set each of these equal to 0 and solve for both x and y. All right, so let me work on the left side first. I'm going to factor this and use the zero product property. 0 equals 3x parentheses 1 minus y. So 0 equals 3x, or 0 equals 1 minus y. Therefore, x equals 0, or y equals 1. Alternatively, on the other side, 0 equals y parentheses x minus 2, if I factor out the y. So therefore, 0 equals y, or 0 equals x minus 2. And so 0 equals y, or x equals 2. Now, what do we see here? What's an equilibrium position? I'm going to go with these two points we have, x equals 0 and y equals 0. This is when we have an equilibrium position. Alternatively, we've also got an equilibrium position when y equals 1 and x equals 2. So let me write that down. The two equilibrium positions are 0, 0, when there are 0 sharks and 0 fish, well, obviously, and when there are, y is in the what? The hundreds, right? And when there are 2,000 fish and 100 sharks. Those are my equilibrium positions. So let's move forward from here. In number 3, it's asking us use the Euler method with a step size of 0.02, look, much smaller than we've been using before, to show that when t equals, oh, I'm sorry, we haven't finished problem 2. Initially, there are 3,000 fish and 20 sharks. Okay, so what we want to do is actually find the equations using the initial conditions. I'm sorry. So what we're going to do is we're going to use this coordinate point here, our 0, 0 coordinate point, because we are given the initial values, all right? So 0, 0 when t equals 0. So what we're going to say is dx dt, remember, equals 3x minus 3xy. Okay, so what we're going to do is plug in 0 for y and solve the differential equation for x. All right, so we're going to have equals 3x minus 3x times 0, and we get dx dt equals 3x. We can now integrate both sides. I'm sorry, we have to get our variables together. So we're going to get 1 over 3x dx equals dt, 1 dt. Take the integral of both sides. All right, and we're going to get the natural log of 3x equals, what is this going to be? T. Oops, that's not a T. T plus C. Now, if you remember back to last week, this sort of always becomes the same thing. It's going to be, what is it? X equals e to the t plus c. And remember, the plus c ends up becoming the coefficient, ends up becoming the coefficient on the exponential expression. So x equals e to the t plus c. And we end up writing that as e to the c times e to the t. Here, we need to put our initial value. So initially, we say there are 3,000 fish. So that means x equals 3e to the t. All right, so without having to go through how to solve differential equations again, flip back in your notes, x is going to equal 3e to the t. Now let's do the same. I'm going to pause and write this out just to save some time. I want you to pause the screencast right now and plug in 0 for x, and find y. Okay, and so if you solved correctly, you should have gotten y equals negative 1/2 times 0.2 e to the t. All right? Now, on the left side, I'm sorry, I forgot to divide by 3, so that 3 divides by 3, and we actually get x equals e to the t. Now, notice the difference in these two equations. The population of fish is showing exponential growth, right? Whereas the population of sharks is showing exponential decay. Notice this a value, right? It's 0.2 times e. It's going to be a value between 0 and 1. Now, let's answer part 3, and I've already done a little bit of graphing around this. So in part 3 it says, use the Euler method with a step size of 0.02 years to show that when t equals 0.02, there are approximately 3,144 fish and 20.4 sharks. Actually, I just realized that this is what the follow-up screencast is about. So I'm not going to continue recording right now. I'm going to let you watch the next screencast, which came from last year, where I'm going to show the graph. We can use the Euler method with a step size of 0.02 to show that when t equals 0.02, there are approximately 3,144 fish and 20.4 sharks. That's easy. You already know how to do that. Just create a table of values and use the formula for Euler's method for t, x, and y. All right? That's going to give us 3,144 fish and 20.4 sharks. What is interesting, though, is question 4 and 5. All right? So in question 4, you're going to see this graph where we've graphed x and y on two separate axes, and we take a look at the turning points as well as the equilibrium points. So I'm going to stop this screencast right here, and I want you to follow the next screencast. Toodaloo.